In this segment, we start to look at a more general problem on a graph that a random walk can solve. We consider a more general scenario than just finding our way out of a maze. We start at the green dot, and we want to find one of the red dots. You can think of the red dots as being the locations of treasure in the maze, and that all of the red dots have exactly the same treasure. So we want to find one of the red dots, but we don't care which one. I will refer to these locations of treasure as marked vertices. We will consider the situation where an epsilon fraction of the vertices are marked. How many steps do we have to do our random walk to find a marked vertex in this setting? Let me be more specific about the game that we will be playing. It may sound a bit strange at first, but we will see that this is the right game for our applications of the random and quantum walk paradigm to query complexity. We assume that the underlying graph is known, but each vertex of the graph will have some associated data that is unknown. In particular, whether or not a vertex is marked will depend on this data. We incur costs for learning the data associated with a vertex and for checking if a vertex is marked. So, because the graph is known, we can perform steps of a random walk without checking the data at vertices. But if we want to check if a vertex is marked, then we incur an additional cost. Let's see how we can find a marked vertex in this setting with a random walk. I will be a bit hand-wavy here and just give the intuition. Again, I assume that our graph is deregular, connected, and not bipartite. We have seen that in this case, if the spectral gap is delta, then after 1 over delta many steps of a random walk, our distribution over the vertices will be close to the uniform distribution. That is, it will be within some small constant in terms of L2 distance. If we truly had a uniform distribution over the vertices, then in choosing a vertex from this uniform distribution and checking if it is marked, we would have probability epsilon of succeeding. Again, this is by our assumption that an epsilon fraction of the vertices are marked. So here's an algorithm. Remember, we want to check to see if a vertex is marked as few times as possible, since this incurs a cost. So what we do is we start at an arbitrary vertex and we do a random walk for order 1 over delta many steps. This random walk is done completely independently of the data that is actually at the vertices. So we incur no cost for doing this 1 over delta many steps of the walk. Only after this 1 over delta many steps do we check if the vertex where we land is marked. It will be marked with probability roughly epsilon, since we are close to the uniform distribution after this many steps of the random walk. To amplify the success probability, we repeat the whole process starting over from scratch 1 over epsilon many times. This procedure will then find a marked vertex with constant probability. The total number of times we have to check to see if a vertex is marked is order 1 over epsilon. Let's formulate the cost in a more abstract way. This will allow us to apply this framework in many different situations. First, there is an initialization cost, S. This is the cost to set up the data at our starting vertex. Then there is a cost, U, to do 1 step of the walk. Finally, there is the cost, C, to check if a vertex is marked. The initialization cost, S, we only incur once at the beginning of the algorithm. We always begin from the same vertex when we restart our walk, so we don't incur this cost again when we restart the walk. The total number of times we check is 1 over epsilon, so we have a cost of 1 over epsilon times C. Finally, we do 1 over delta many steps of the walk in each repetition, and the total number of repetitions is 1 over epsilon. So the total update cost is U times 1 divided by quantity epsilon times delta. This is all fairly abstract, so let's look at an example. Let's say we want to solve the element distinctness problem. We are given a string x with n letters over the alphabet 0 through m-1. We assume that m is at least as big as n. The question we want to answer is whether or not all the entries in x are distinct. We again think about solving this problem in the query model. So we can ask what letter is at the ith position of x, and we want to figure out if there is a repeated letter in x while making as few queries as possible. We are going to try to solve this problem via a random walk. The graph that we are going to walk on is known as the Johnson graph, and it is parameterized by n and r. The vertices are all r element subsets of 1 through n. And two vertices are connected by an edge if and only if their intersection size is r minus 1. So they are connected by an edge if one subset can be transformed into the other just by exchanging one element. As long as r is not too big, it is known that the eigenvalue gap of the Johnson graph is theta of 1 over r. Remember that the vertices of the Johnson graph are subsets of 1 through n of size r. For a vertex labeled by the subset T, the associated data is the values of xi for I and t. We say that a vertex T is marked if there are I and j and t that are distinct and such that xi equals xj. Thus, a vertex is marked if it witnesses that x has a repeated letter. If we already know the data associated to a vertex, then the checking cost is 0. The setup cost is r because it takes us r queries to x to learn the values of x in a subset of size r. Now here's the neat thing about the Johnson graph. The update cost is just 1. Since the subsets of two adjacent vertices in the Johnson graph just differ on one element, if we know the data associated with one vertex, we can learn the data associated with an adjacent vertex with just one more query. Now let's compute the overall cost for our randomized query algorithm for element distinctness using a random walk on the Johnson graph. The fraction of marked vertices is omega r divided by n quantity squared. You can see that because this fraction will be the smallest when there is exactly one repeated letter. The number of sets of size r this pair will appear in together is n minus 2 choose r minus 2, which is roughly an r divided by n quantity squared fraction of all of the n choose r many sets of size r. Let's plug these values into our formula. The setup cost is r, the checking cost is 0, since we always maintain full knowledge of the data at a vertex when we arrive at that vertex. The update cost is 1, so the total cost is r plus 1 divided by quantity epsilon times delta times the update cost, which is 1. So the whole thing is r plus n squared divided by r squared times r. Now this turns out to be not very interesting. It is minimized just by taking r equals n, which is the trivial algorithm of just querying all of x. In fact, we can't hope to do anything better for this example of element distinctness, because we also have a randomized query complexity lower bound of omega n. But the reason why we have gone through this example is to motivate the quantum case, where we will construct a direct analog of this randomized algorithm of a random walk on the Johnson graph. The analogous quantum walk turns out to give something very interesting for element distinctness, and we go over this in the next video.